Hello?
Hello? Is it me you're looking for? I see it in your eyes. I gotta make sure the sound is actually working this time. No, like on one of my classes, I accidentally unplugged the microphone.
All you hear is just silence.
I know, like, yeah. Some of my best jokes were in that class. Anyway, alright. Okay, listen, you guys. Okay, first order differential equation. The function is f is continuous on its domain. Continuous on its domain. What does that mean?
So it don't stop.
It don't stop.
It doesn't have holes or asymptotes.
Thank you. Yes, has to be continuous. That's what the issue is here. A set of points in the xy plane, each point x sub naught, y sub naught, in the domain of f, we can evaluate f of x sub naught, y sub naught, and determine the dy dx of f of x sub naught, y sub naught. The slope of the tangent line to the graph of the solution to the differential equation at x sub naught, y sub naught, if we draw small line segments representing the tangent lines at every point in the domain of f. The resulting display is called a slope field. Gives a picture of the family of curves that make up solution of a differential equation. All possible different values of c. That's basically it. We're plugging in x and y and find all possible different values of c. Use slope field to represent the differential equation dy dx equals y. Use slope field to represent to draw some graphs of the family solution here. Okay, so now I gotta try and remember this one on the calculator. The calculator is actually funny on this one, so I'm going to go here, here, menu.
It's like rain.
Okay, so slope of 1, so that means at all points my slope will be 1, right? Does that make sense? Okay, from right here, let's go back up. And I'm going to make it x when I have there we go. Okay, here's of x, all the different possibilities. So whenever I plug in x, it keeps just getting bigger. And then I'm going to go to another one right here. Change this one to y.
Yeah, whoa. Yeah, who's that Hakuna Matata guy?
What kind of math are you doing?
The meth of
There is no worries.
yeah.
For the rest of your days, yeah.
It's the exact opposite.
Yeah.
Run. See, why is it gonna be like this to me now?
Going to the bathroom again?
All right,
Gotta go,
so
you gotta go.
Yeah, when you gotta.
trying to remember how to actually enter this one in specifically. Let's go from negative.
You still, his math never gets shown. You got like the short end, but they do. Euler always gets, his name's always paraded. It is always just it's like a nobody.
Okay, so this one right here gave us a particular solution. When I had -1 and 2, it followed this graph right here for this.
Oh, okay.
So that is my particular solution there. And so I'm going to menu, go right here. Let's just go -2 as my window to +2 to make this easier, because when you guys draw this by hand, oh, it's gonna suck. Finding out all these, they do pop up on the AP test. And I want 1. 1. So it's not so big. So in between here and here, so you could actually see all these, and it had a particular solution for this one right here.
When do you actually use slope field in
So like the problem we did.
No, I'm actually curious.
No, the problem that we did. So let's say, for instance, it said, what do we get?
Just told us to do it.
Y
Nobody
is
said this.
x squared over x
We're not projecting against some planes anymore.
x to
Yeah,
the
we're in a whole new level.
4th over 16, and my particular solution was 1. X was what? X was 2. Y was 1.
That's so cute.
It's a line.
But like it looks like
It's all the points right here. This is the particular solution of this right here. So this is the solution that I have right here for this. Alright, so let's take a look at, trying to remember how to enter it in specifically for that one. Like if there's a y value. Go times, I think it's times y.
Ooh. Yeah.
Y times.
Why does he get a dot but on my calculator? It's a giant asterisk. Unless I pressed the wrong button. No, I didn't.
Is it an F? I can't remember how to do this, dang it. I did this like yesterday just so I could like brush up on the calculator, and I totally forgot how to enter the y part. Anyway, alright, let's go back to this. Slope field will represent the differential equation here to here. So, now, what's going to happen? So, for all my x's, so let's say for instance, plug in my points. So, do my x's matter at all? Okay, so I'm going to make a small one right here. Let's go. So, when x is -1 and y is 0, this is going to be
The slope is a 0.
at -2. What is my slope? -2 and 0?
It's gonna be 0.
And let's go 0, 0. Okay. What do you think 1, 0 is going to be? And? Okay. Let's try next one. So let's go, let's see, -2 and 1. 1. Slope is 1. -1 and 1.
1.
That's a tricky.
Yeah.
So it's all gonna go like this, right?
the X really plugs in weird there.
Yeah, the X really plays the contract.
Okay, what about 2? If I do like this, let's go negative 2 and 2.
Slope is going to be 2.
Same thing,
Yeah. When we drew this on the AP test, like, it was so annoying.
right?
This stuff.
Okay.
It's like, I need to read it.
Now, let's go down to the negatives. Let's go -2 and -1.
So -1 slope.
All the way?
Yeah.
And
And it's a -2 slope, no matter why it's -2.
we just created a slope field for that. Now, the really big important thing to understand is, look at the shapes. From that graph right there, can you look at it and tell that the X had nothing to do with it? If the Y's are always going to be the same thing going all the way across, that means the X's don't matter. X's don't matter. So that means that I can come back and be like, okay, if it's the same going all the way across, that means that there's X not going to matter. What if it's the same thing going up and down like that?
The Y won't play that.
The Y is not going to matter. Does that make sense?
Yeah.
That's like key for a lot of these problems right here. So, okay, draw. We have a family of solutions for this one right here. So, represent that equation. All right. So we have all this for this, right? So when I do this and I find the equation, let's separate this out. So let's do, so it's going to be dy dx equals y. So I get dy over y equals dx. So I get, what's the integration of 1 over y? ln y, thank you. So it's going to be ln absolute value of y, right? Equals x plus c, right? So move it over. So it's going to be negative x plus ln absolute value of y equals c. Or in this case, whatever value I have, plus c equals 0. So for this one right here, I could actually solve for c given any of those solutions. So I could plug in x and y here. So if I plug in 0, 1, if I plug in 0, 1, what should I get? What would our slope field right here say? It should be 1, right? Okay, let's plug in 0 and 1. So, right here, 0x, ln 1, 0, c equals 0. Okay. So I get c is equal to 0 on that one right there. So I would have a particular solution for that one. Okay, I could just keep going through and actually plug in each one to solve a c for each one of those. So I can get a specific solution. So I'd have a function that looks like this that's going to match something like here. It's going to go through this. Which of the following differential equations could have a slope field shown? Why C?
Because y doesn't matter for it, and it's all,
Yeah, because if you look at
it's not.
column wise, vertical,
Okay.
y doesn't play a factor.
Y does not play a factor. It's not going to matter there, right?
And in the direction of the slope shows us.
Yeah. So it should be positive, right?
Yeah.
So now, if you think about it, so if it was a negative x, that means a negative and a negative. So when I plug in the negative x's on this side right here, that would be a positive, wouldn't it? That would be a positive if it was going to be the negative x here, right?
Yeah.
Okay. So it would be going the other way. So it would be upside down for this one. Makes sense? Hopefully? Okay. Euler's method to approximate a particular solution, first order differential equation. Euler's method is a numerical algorithm for approximating particular solution, y equals y of x of a first order differential equation, dy dx equals f of x comma y, with the boundary condition that y is equal to y sub naught when x is equal to x sub naught. It begins with the boundary condition x sub naught comma y sub naught and a small arbitrary increment h in the x. The first approximation to y equals y of x is given by y1 is equal to y sub naught plus h times f of x sub naught y sub naught. The second approximation uses y1 from the first approximation, and x sub 1 is equal to x sub naught plus h, which would be the little increment I'm adding each time. Okay, so I'm approximating, so I'm adding a little bit more to this to actually keep getting it. Okay, each successive approximation follows the same pattern. Third approximation uses y2 and x2, okay, where x sub naught plus 2 times h and so on. So it keeps going. So eventually it comes up to some number over here, like this, where I'm actually plugging in those, where it is 1 less, okay, 1 less. I start with my initial, then keep going, I'm adding h. So if you think about it like this, so I'm going to keep going for each one of these. So, and so on. So, each successive approximation follows a tangent line to the graph of the solution to the differential equation. That is, it follows the slope fields. So, it's basically what we just did, the approximation with the line through there on the graph. Okay, where I get h, which is going to be some increment that I'm adding to my x, which is going to give me this one here. And then over here, it's going to give me over here on this side. So it just keeps going right here where the red line is going to be my tangent line at that point, x sub naught, my original. Suppose y is equal to y of x, the solution to the differential equation is here, with the boundary condition that y equals 2, x equals 1. Use Euler's method to approximate y of 1.5 using increment of h of 0.25 as the increment. Okay, so let's go through and separate this bad boy. Oh, let's see. What should I start by doing? What do we need to do first? Let's separate this. How can we separate this? Can I separate it? Serious question. Can I separate that? Okay, so let's start off with y of 1.5. What does that represent? What's that represent? Okay, it is
First time, so.
okay. I have my x and y, right? And I'm trying to approximate that one. So, what's that going to be? So the first order would look like what? Let me just carry that over. And it should be, what was it? It was y1 equals y sub naught h f of x sub naught. Okay, what do we know from this one already? I know h. What else do I know? Okay. And do I know x sub naught? Okay, so there's my conditions, right? So what am I doing with that information? Okay, let's do that. If I plug it in, where are we going to end up at? Aren't you get what?
Wait, you don't need to separate it and integrate it for the f of x sub naught y sub
No,
naught?
we're not. For this
Okay.
one right here. That's what I was asking at the very beginning.
But
So
I
if
was
we were
just
trying to
curious-
separate it, we couldn't separate it, right?
Yeah, well, it's just because it's like f of whatever, but that says that's the derivative, dy dx.
Mm-hmm.
So it's somehow
Yeah.
just messing
So
with
slope
my brain.
field. So we're figuring out all the slopes for all the
Yeah.
points in between
I
there.
know, it's just like, it's like f of x, but.
Okay. So this is of 1, right? What is my x value of this, right? My x value was what? Y of 1, right? And this should be 3, right? What's that going to give me? 11 fourths, right? Or 2.75, right?
I think you hated decimals.
Huh?
I thought you hated decimals.
I do. That's what I'm like, okay, for the people that actually do. So 11 over 4. It's going to make math easier if we have it like that, right? Here's the first one, right? Okay. So now what are we going to do for the next one? What's the next part of my increment? Nope. What is my next part of my increment? How much is it going? 0.25. So this next one's going to be what?
That plus
Y of 1.25 is equal to
Equal to y1, so 11 fourths
11 fourths
plus
Alright? Did I lose you? Did I lose anyone?
I don't think you have a sound.
Oh, let me see. You got the stunner shades on again, so yes, I can still see you. Okay? Just because you can't see me doesn't mean I can't see you. Go ahead.
I'm still confused for f of x of naught, y of naught.
No, all this means is plug in x and y to your function.
So is it
What do we have? We have this right here, right?
The functions you get.
Yeah, from there. So plug in this x and y into this.
Yeah, it's kind of expected.
So now this one's going to be, it's going to be f of 11 over 4, comma, no wait, it's not 11 over 4, that's next one's going to be 1.25, and I'll plug it in 11 over 4. Or 5 over 4. Is that easier? 5 over 4? So if we're plugging those in, it might be a little bit easier. So I'm plugging in the x and y that I have there. Yeah, so this piece right here, so when I'm plugging that in, that, go ahead, say it again, that would be what? So 5 over 4 times 11 over 4 plus 5 over 4 squared.
11 over. No, yeah, 5 over. So it would be 55 plus 25 over
So 55 over 16
plus 25 over 6.
plus 25 over 16 is going to give me,
80 over 16, which is just 5.
what is it?
80
5.
over 16, which
Wait.
is just 5.
Which is just 5. So it's going to be 5 over 4, right? This is 5 over 4 plus 11 over 4 is going to give me 16 over 4, which is what do we say that was? This is 5 over 4. Y of 5 over 4. And we're trying to approximate to what? 1.5, right? We're trying to approximate to 1.5. I'm almost there. My next increment is going to take me there, right? So each increment is going to go on. So I put in the previous. So now this is going to be the increment of y is, what's that, 3 over 2? Y of 3 over 2 is equal to my 4 plus 1 over 4 times my function. Now in this case it's going to become, I have f of 5 over, nope, 3 over 2, comma, what was my previous one, 4? There we go.
No, I get it.
So plug it back in. So I'm over here now. So that's going to be 6 plus, what's that, 9/4. Add that together, that is 6 times 4 is 24, plus 9 is 33 over 4. Yeah. So y of the 1.5 or 3/2 is going to be equal to 33 over 16 plus 64 over 16. 97 over 4?
Yeah.
No, 97 over 16. There you go. So 97 over 16, which is approximately, hopefully 6.065. Yes? Yep, there we go. So, more work on this, okay? Now, on Monday, we need to start the first part of the final. Okay? So, now, there is